In this video, we're going to discuss how to prove logical truths in Fitch-style system. Let's get to it. So if you'll recall, logical truths are logically necessary, which means it doesn't matter what the situation is, a logical truth will be true. And since it doesn't matter what the situation is, its truth does not depend upon any other premises. So we should be able to prove logical truths without appealing to any premises. And in order for Fitch-style system to be a good natural deduction system, there had better be rules that allow us to prove logical truths without appealing to any premises. So this is one example, and what we're going to do is we're going to turn to the Fitch computer program to show, and I'll show you how it is that you can prove this proposition without appealing to any premises, and we'll actually look at a second example as well. Alright, so here we don't have any premises, but what I would like to prove is that A is numerically identical to A. And if you'll recall, A in FOL is an individual constant, which means that it refers to an object, but it can refer only to one object. Unlike, say, for instance, the name Bob in English, in which there are several people named Bob. There is only one object in our discourse that is named A when we're using A in FOL. So to say that A is numerically identical to A, since A can only refer to one object, it turns out that that has to be true. There's no way for A to be something different than A. And we do in fact have a rule that allows us to assert that A is identical to A, or as it were, B is identical to B, or C is identical to C, and so on and so forth, as long as we're dealing with individual constants. And that is identity introduction. We don't have to cite anything. It just always is true. All right, let's look at another example of proving a logical truth. All right, so what I want to prove here is that it cannot be the case that A is true and A is false. This is the law of non-contradiction. All right, to do that, I'll notice that what I want to prove is a negation. And thinking about the fact that it's a negation, I ask myself, are there any rules that allow me to add a proposition that is a negation? And the answer to that is yes. Negation introduction allows me to do that. And if we'll recall, the way that negation introduction allows me to do that, and we can actually see that by looking at the rule here, is by assuming a proposition and then showing that that proposition generates a contradiction. If by assuming a proposition and it generates a contradiction, then I know that the proposition that I introduced has to be false, and therefore the negation of that proposition has to be true. So I'm going to employ that strategy. In order to employ that strategy, I'm going to add another step and then make it so that I'm introducing the assumption. The assumption that I want to introduce is the one that I want to show is false. And what I want to show is false is A and not the case A. And looking at A and not the case A, I can see that I can get a contradiction fairly easily, because if I can pull out A and then individually pull out not the case A, that takes the form of P and not the case P, which just is the form of a contradiction. Well, I can pull out those conjuncts through conjunction elimination. So I'm going to do that. Now that I have A and not the case A, I can introduce a contradiction because these take the form of P and not the case P. I do so by using contradiction introduction and citing the propositions that contradict one another, and now I've introduced the contradiction. Well, hey, that's just what I wanted to do. I wanted to assume that this was true and try to prove myself wrong, and this contradiction tells me that I am wrong for introducing that. And so this proposition must be false. Well, how can I say that that proposition is false? I add a negation to it, which is what is happening in step 6. And if you'll recall, the way that we do that is through negation introduction, which is the same thing as proof by contradiction, or also known as indirect proof. We check it out, and indeed, without relying on any premises whatsoever, we can prove in Fitch-style system that it must be true that it's not the case both A and not the case A. And since there aren't any premises, what that tells us is that no matter what the situation is, there can never be a contradiction. Alright, that ends this video on how to prove logical truths in Fitch-style system. I hope you found it useful.